Good afternoon. Thank you for being here. I understand machine learning after lunch is not probably the most digestible topic, but the idea is really to give you an idea of how a developer that has not a great experience in machine learning can start to use it in our own applications. So if there are any data scientists or PhD in machine learning, I already apologize in advance for the simplification that I will do during my presentation. I truly think machine learning is going to change, together with artificial intelligence, that is probably a broader topic, our lives in the near future. In the next 5, 10, 20 years, a lot of analysts, and I agree with them, think that machine learning and artificial intelligence would be comparable to the impact of the Industrial Revolution a couple of centuries ago. So new jobs will appear, old jobs will disappear, and I think this is a very good topic for developers to be updated with. So when I talk about how you can make data predictions, this is a picture that I always like to look at. Does anybody know what's in this picture? This is March the 8th, 1939, and there's people counting by hand 4 million tickets of the London Underground. This is a big data project 80 years ago. And of course, the term big data is always relative to the technology that is available. And this is something that was done to optimize the underground, to understand which routes were used, which not, how to create new ones. And we see that our customers also today start in this way. They start looking at data that they save, building reports that are batch, so they build a report every month, every week, maybe every day, and try to understand the data with data visualization tools. From this, customers, they try to understand what is happening right now, not in the past, like with batch reports. And they want to do real-time analysis, understand now what's happening in my support, in my deliveries, in my call center. And after that, the next phase is that they want to look from the past at the present to the future. They want to understand what is going to happen tomorrow, next week, in 1 month, so to create a forecast of their activities. And how do you build predictions? To build predictions, you have the data that you can save today and relative to the past. You want to build predictions of the future, and you need to build a model. A model is a way to abstract from the data how the things are happening. So it's an abstraction that allows you to create new things, new predictions for the future. So how do we build this model, since it seems to be the interesting part? Well, currently, most of the technologies that has been developed in the latest 10 years is using the term machine learning. So the idea is to create a program that can learn from data, find the patterns in the data, and use these patterns to create the model. There are 2 kinds of machine learning algorithms. One is called supervised learning, and one is called unsupervised learning. So with supervised learning, what it means is that you have labeled data. So for example, let's say that I want to create a weather forecast application using machine learning. I can have all the data of the past. So I know that in this location and in all the surrounding location, what was the weather, what was the temperature, the humidity, the eventual rain. And then from this data, I want to predict the rain, the humidity, the temperature for tomorrow, 1 week, or maybe even further in the future. So I have labels that I can use to abstract the data. With unsupervised learning, you have data that is not labeled. So you have data that really has no way to abstract the information that you want, and you want to extract some inner relationship within the data. I will make more concrete examples very soon. Some people say there's a third way of learning that is reinforcement learning. Actually, this can be part of supervised learning. The idea here is with reinforcement learning is that you have a dynamic environment. So this is how we learn as people. We don't have a period of learning and then we stop learning and we just do things. We continuously update in a dynamic environment what we want. So there is a way of reinforcing, giving a feedback, and adapting the model as soon as more data is available. So this is an example of how you can use reinforcement learning. So a couple of days ago, Tesla released a video of a self-driving car that was driving from one house to the Tesla office completely by itself without anybody touching nothing inside the car. And of course, this is kind of reinforcement because you have to learn from mistakes, update continuously depending on what is happening in the surrounding area. Generally speaking, every game is a reinforcement learning, can be seen as a reinforcement learning when you have a concept of score and you want to get a higher score than your opponent. With unsupervised learning, the most common type of analysis that is done is clustering. And by clustering, we mean finding internal groups within the data. This is something that has been done for lots of years, even before the term machine learning was popular. For example, large companies that have, for example, millions of customers, they usually want to understand if these millions of customers are actually grouped in different groups, are part of different groups. Maybe there's a group of young people that is using only this kind of services, a group of older people that is using more traditional services. And understanding your customer after using clustering allows you to then maybe improve your services or create direct marketing campaigns. So for example, here you have a lot of points, and these points can be split in these three groups. This is probably the most natural way to split these points in three groups. Visually, it's very easy to do, but you have to think that in a normal machine learning model, you don't have 2 dimensions, as here. You have points that move in hundreds of dimensions. For example, you can have customers that have an age, have a job, have a different address, have a different history of using your products, and so on. So it's much more complex. And each point here is just showing a couple of dimensions. So think of the abstraction in multiple dimensions. With supervised learning, so when you have labeled data, there are 3 kinds of analysis that are very common. One is regression, when you want to predict a numeric variable, like the temperature, like the number of bike that will be available in a bike sharing station. Everything that is a number can be integer or real. Classification is another hot topic. Binary classification is very common, so you want to classify someone compared to 2 classes. For example, if you are a company, you want to understand if this customer is a customer that is going probably to leave your company very soon, or is a loyal customer that will probably stay with your company in the next months. Or multi-class classification, like when you have not just 2, but 3, 4, 5, 10 class, classifying a movie by genre. So you can have comedies, you can have a dramatic movie, you can have historical movies. So this is an example of multi-class classification. One important step when you build a model is to validate the model, because when you start to look into machine learning, you find beautiful and complex and interesting algorithms. You can create the most complex structure in the world, but then you need to understand if you are actually improving compared to a baseline naive approach of maybe just guessing randomly or statistically what is happening. So one important step in machine learning is that you have, I'm talking about supervised learning here, if you have all your data, 100% of your data, you must create the model. The term is train the model using only a subset of the data, usually 70, 80%, and keep some part of the data apart as validation. That means that you will create the model using the training data. You will apply whatever algorithm you want. And then the result you will test on the validation data to see if this model is capable of predicting the validation data that never touched the model before. You can't test the model on the same training data that you use to create it. Otherwise, it will be biased, and it's very easy to get good results that don't work as soon as there is a little bit of abstraction that the model must do. And the risk here is the risk of overfitting. This is a very practical risk with machine learning, and I want to point you to that because let's look at these points here. And let's say that I want to understand the relationship of these points. If I overfit the data and create a very complex multi-polynomial algorithm, probably this is a perfect fitting. This curve is a perfect fitting for my data. It fits perfectly. It's passing in the middle of every point. And if I use this curve to create prediction, I can predict, for example, these 2 results here. So let's imagine that this is the temperature of the weather in the next few days. Maybe in the future. In the past, it's difficult. But if you look at the points here, let's say that you have time on the x-axis, and then I can predict that the temperature is corresponding to the values where the lines is crossing the curve. But numbers in nature are never exact. There's a lot of errors in measurement, in the way you collect data. So probably a much, much better fitting for this data is this line that is never passing in the center of any points, but is a much simpler model, is getting closer, and it's giving completely different predictions than the previous model. So the first one was an example of overfitting. This one is probably maybe too much a simplification, but it's probably much more useful than the other one. So now we have the data. We want to build the model. How can we build the model? This is the nice part. Nowadays, there's plenty of tools available that you can pick up, choose, and play with. One tool that is getting very, very popular for machine learning is Apache Spark, that has already been mentioned during this conference. And Spark has a specific library, the mlib, for machine learning, with a lot of machine learning algorithms available. So let's see how this would work. So for this example, I'm using Apache Spark running on Amazon Elastic MapReduce. Is our engine that can support clusters of Hadoop, Spark, and the related ecosystem. And one of the tools of the Apache Hadoop and Spark ecosystem is Zeppelin. Is a visual notebook. Is similar to IPython or Jupyter, if you know them. So, and it's the kind of tools that data scientists really like, because you have a web interface where you can put computation and you get results dynamically. Here I created what is called a notebook for a recommendation engine. So what I'm doing now, I'm using a standard data set. So in machine learning, people over the years created multiple standard data sets with different case studies that everybody can use so that you can compare your results with the others. If the data is always different, then you don't know if you are improving or not. So if you use a standard data set, you can see if you are doing better than another algorithm or your results are worse. So in this case, I'm using the movie lens data set. That is a very popular data set where you have lots of movies, lots of recommendation of this movie. So people is saying how much they like the movie. And you can try to use this data to extrapolate what other people think of a movie. So what are the movies that people can like? So this is an example built with Spark. Spark supports multiple languages. I'm using Scala, that is one of the native ones here. So I have the data on Amazon S3, so this is the path of my data. It's not important to understand the details. I just want to show you the overall flow. So I load the data from the movies and the ratings file. So the movies contains all the movies, and the ratings contains the ratings that people has done on the movie. So I like this movie or I don't like. And here I count the value. So we have roughly 10 million ratings here. And we have 70,000 users and 11,000 movies in this database. Now, what I do is exactly what I said before. So I split the data in training and validation because I want to create a model. So I need to split the data because if I don't have this separation, then I don't know if the model works or not. So I split the ratings, 60% for training, 20% for validation, and I keep another 20% for a final test that I want to do, if I want to do it. This is another recommendation that lots of people is doing. Now I need to measure if my model works or not. So usually you create an error function that will estimate how far you are from a correct prediction. And in this case, I use the root mean squared error. So I'm creating this function. And this is the core part of the training. And I'm using the alternating least squares ALS algorithm that is provided by the mlib library of Apache Spark, so I don't have to write any complex algorithm. And what I do, I create a list of different parameters, and then I try to train the model with different parameters, test the result on the validation data, and see how far I am with the error function. Doing multiple iterations, I can change the parameters of my model and see which parameters work best. It's important that I train on some data and test on the validation data that never touched the model before. So I create here a list of different options. Then here I have a loop where I use this als.train command to train the data depending on the model. Then I compute the error of this model, and then I display it. So here you see all the permutations, and you see the error is different from, of course, the absolute value of the error depends on the scale that you're using, so it's meaningless, but the smaller it is, the best it is, because it's a positive value, it's the sum of squares. And here I get that the best result was with these options, and this is the smallest error that I can get with these parameters and this algorithm. Now, what I do, I want to be sure that I'm doing something useful and I'm not losing time. So I create a baseline, very naive approach. So let's say that for every movie, I give the average rating that the people is giving to all the movies. So I look at all the ratings. Maybe the average rating from 1 to 5 is 3.2. I give 3.2 to all the movies. I want to be sure that my complex model is behaving better, so giving a smaller error than this very basic approach. If not, probably I'm just creating complexity out of nowhere, and it's just vaporware. So here I get I create this model that is just taking the average rating and using it always. And the result that I get is that my model is improving the result of the baseline by 22%. So the error is smaller than 22%. Can seem not a lot, but it means that I'm doing something. If here that number was negative or very close to 0, probably I'm just wasting my time. And now I can extract information. For example, I can go in the recommendation and say, give me the recommendation for the user ID 100, that is one of the 70,000 users, and I get the 10 movies, the top 10 movies that he would like. So there is Maradona by Kusturica, there is Pulp Fiction, The Godfather Part 1 and 2. So it's probably quite an interesting person. And then I can filter my recommendation only by genre, and then get only the comedies, and then get only the list of the top 5 comedies. So there's Dr. Strangelove is even another more interesting movies here. And in this way, you can start exploring the data and maybe move to a data visualization tool to understand how this works on a larger scale. So this is how you would build a machine learning algorithm using Spark. It's relatively easy. It's not the easiest thing in the world. So let's see what we did in Amazon. By the way, if you're interested, I will leave the slides. The algorithm that I was using is described in this article here. So we saw how we can use EMR and Apache Spark to build a recommendation engine. But there is a problem. The problem is that developers are starting to be relatively common, but data scientists are not. So within a company, having a lot of data scientists is difficult, and you still need a data scientist to build and choose the algorithm, evaluate the error. So how can we proceed? In Amazon, we realized we couldn't have a data scientist inside every team because we have a lot of projects and it was not scalable. So we decided to create a platform that we created inside Amazon. We used it for years. And then last year, we made it available for everybody to use. That is Amazon Machine Learning. And this platform is designed to be used by a developer that doesn't have the knowledge of machine learning that a data scientist can have. So it's designed to be very simple and can build batch predictions. So you can give some data and get a batch of predictions. Or can also do real-time predictions that you can embed in your applications to build real-time models. This is some information on the algorithm that we use, nothing that we should spend so much time now. But maybe it's interesting to say that we cover binary classification, multi-class classification, and regression. We will do an example with binary classification. So let's see a demo of how this different approach using our platform works. So in this case, this is the AWS console. We have the analytics part where we have machine learning. And here in the machine learning console, I can create a new data source, that is the data that we need to train and build the model. and then the model out of this data. You can have the data as a file, and you can use our object storage, Amazon S3, or you can have the data on a database, such as Amazon Redshift is a data warehouse database. In this case, I have the file already loaded, and it's in this bucket here in Europe. And it should be why doesn't so the network, there should be network. This is the demo effect, so let's reload the page, maybe something. I love doing demos because it keeps me fit every time I lose some weight on stage, and it's the best way to. So I know the path should be this, but it's not loading. Nice. So I have the file here, so we can give the file. So it's banking.csv. And this is, let's call it Greece banking. Let's see if validation. Maybe the name is not the best. Let's call it banking 2. But it seems that there is some network connection issue. I don't know why, because I tested everything before. So we have 4G. The connection, so maybe with my hands in the hair, it's easier. Last test, otherwise we can see the result because I downloaded the result for a backup, but it was, seems to be more reactive. It's this part here where it doesn't want to. No way. Not moving forward. So let's cut it short. So I have the file here. So this is the file that I was trying to upload. And this is, maybe it's my computer that is running slow. OK, this is a CSV file, so it's comma delimited. And I open it with Excel, because it's not a huge file. And this is a case where you have a bank, you have a few users of your bank, and you try to call them or reach to them to see if they are interested in a specific product. So you have all the information, the age, the kind of job, if he's married, if it was contacted on the phone, on the cellular, or using other means, the time of the day, and the day of the week you contacted this person, all this kind of information. And at the end, you have a 0 or a 1 in the last column that tells you if this person bought the service, so it was interested in this product, or not. So if you give this to the machine learning platform, and you tell the machine learning platform that the last field is the field you want to predict, and the other one are the variables that you use to build the prediction, our platform will automatically build the model, and then evaluate, splitting the data in training and validation, evaluate the model. So let's see if at least we can see the validation. So we have this evaluation here. If I go here, it's faster. Not very good. Maybe we will have more time. The network is not working. So the idea is that you can see how this works. And data processing complete. No, this is data sources model. And let's see. No, model. I'm in the wrong region, sorry. So it's not the network, but it's me. OK. So now I think we can work. And actually, we can load the data. So I was just trying to do the wrong thing. So let's say that this is the bucket. Now it works. This is the banking, and here I have this banking CSV file. It's the same file that we saw I was logging, so let's call it banking2. And now it's checking the permission. If the file is readable. In the first column of the CSV file, I have the name of the fields. So now I have all the fields that you saw on Excel: age, job, marital status. And the tool is already trying to discover automatically if this is a number, a category, if it's a string. And sometimes you need to fix. For example, if you have in another data set, I have the season as the number from 1, 2, 3, and 4. So the platform will never understand that this is a season, so it thinks it's a number, but it's better to put it as a category because you know that there are only 4 seasons and you can have season 5 in the file. And this is the part where you should look at the data. So for example, if you have a date, like today is October the 21st, this is an important information, but the day of the week sometimes is important. If you are trying to predict traffic in a town or the use of bike sharing in a town, knowing if it's a Sunday or it's a Friday or it's a Monday is important. So extracting the day of the week from a date is something that is very complex for a machine learning platform. So what you can do, and it will improve your results probably, is to add another the column is what we call a feature in machine learning, where from the date you extract and write the day of the week as a number from 1 to 7, for example. In this way, the platform has this information and can use it. If you don't do that, probably you need a lot of energy, a lot of CPU to get similar results, but at the end, the prediction will not be important. This specific phase is called feature engineering and means that you should look at the data and understand which information could be complex for a machine, obvious for a person, and extract and create this information in a structured way in your data. So adding the day of the week out of a date is probably the most basic example. And here I can continue, and I have to tell which is the field to predict is the final column, the Y, that tells if the customer is buying or not the product. Now I can continue, and I can use the default setup, otherwise you can change and fine-tune how the algorithm works. Usually the idea is you start with the default, and then eventually you can do other iterations. Now I'm building the model, and the model will be automatically evaluated to tell me if this prediction works or not. So now the model is pending. If we go on the dashboard, we see that there's banking 2 has been uploaded, splitted in, this is from 0 to 70%, so it's the training data. The 70% to 100 is the validation data. The model is being built, and when the model is built, it's evaluated on the validation data to understand if it makes sense or not. So I already did it a couple of days ago, just for because it takes 5-10 minutes, since the data set is not big. And here you can explore the performance of the model. So this is a binary classification. You want to know a 0 or a 1, the user is buying or not. And the way you measure this is with the area under the curve, and you get this information. So on the validation data, 91% of the predictions are correct. This is a very high number for machine learning. Usually you get 70%, and it's already a good number. So you know that this is probably some data that I prepared for doing a live demo, and I wanted everything to work. So 91% are correct, 9% are errors. And one very important thing is that errors, in this case of a binary classification, can be of 2 types. Can be false positive or false negative. So false positive means I made a mistake. I thought that this user will buy the product, but it will not. The opposite is a false negative. This user, I predict, is not buying the product, but it's actually buying the product. So why these 2 kinds of errors are important? Because you can change the threshold that is moving errors from one side to the other in the tuning of the model here. And if you want more false positive or false negative, depends on your use case. So for example, let's say this is a spamming algorithm. So you give an input to the email, you want to know if the email is spam or not. This is binary classification. Maybe you are a user receiving thousands of spamming emails every day, and you say, okay, I want all my spam to be removed. If sometimes a few emails are recognized as spam, and I lose them, oh, it's okay, maybe they will write me the email again. And this is your perspective. Maybe this is the email of a company that is receiving orders from customers, and they say, no, I want to remove spam, but I never want to lose an order from a customer because it's money for me. So I prefer to have a few spamming emails, but never lose a real mail from a customer. So even in the same use case, different perspective can change how you want to balance between false positive and false negative. Another example that is very important is if this is for medical reasons. So sometimes you don't have the money to test maybe a large population of people against a possible illness. So you can use machine learning to filter and then test only the people that is at risk. So in that case, probably it's better to test someone that is not actually at risk than to lose someone that can then become ill. So this is another more important use case where false positive and false negative have a different role. So you have to look, and this really depends on your use case, and then you can balance the threshold. And now you can use data like this. So I have here an example. This is the same file as before, but I don't have the final Y column. So this is other customers of my company, and I want to understand who can be interested or not in this product, and then maybe I can give this to my contact center or send an email to them to contact them, because I know that these people will be interested in this product. So what I can do, I can build a batch prediction. So if we go on the model, we are still building this model, but here if I select the model that I built the other day, I can go here and I can generate a batch prediction. I can give this batch file. So this is a banking to batch. So this is the bucket, the banking, and the banking batch. The first line is the CSV. I can verify the file, continue, and now I'm building the prediction. I can write them on the same storage, in the same directory. It's okay. Review, and start the prediction. So just to let you understand the cost of this service, building the model costs $42 per hour, and usually 1 hour is a lot of computation. And building prediction costs 10 cents for 1,000 predictions. So it means that with $1, $2, you can experiment and play with machine learning without being an expert. Now, the result that I would get, it will be something similar to this that will tell you for all the item, it will give you if a 0 or a 1, so the prediction. And this is actually the exact number, and the threshold that we moved was, depending on this number, creating a 0 or a 1. So this is to give you an example. The interesting part is also that you can build real-time prediction. So when you have the model, you can enable real-time prediction, and then you have an API. So I create the endpoint here. And then you have an API that you can call, giving dynamically this number, so the job, the age, all the parameters that I have. So I can, for example, okay, let's not do it, but you can cut and paste the CSV file here, and then it's automatically pasted. And this is an API that you have in Java, JavaScript, Perl, Python. No, Perl, no, we don't have the SDK in Perl. Python, C++. And then you can integrate this API with your application. For example, you can dynamically check, okay, maybe this is the call center application. When a user calls, you call the API and see if you can be interested or not. And then you can eventually notify the call center and say, okay, this user may be interested in this product. Maybe you should mention to him. And this is how you can use this interactively. So let's go back, because we have still some more content. So this is how you can use our platform. You don't need to be a data scientist to do that. But another topic that is very hot nowadays is deep learning. So deep learning is actually an old concept that is now available again because the technology is allowing us to do these kind of things. And it's the neural networks. Neural networks is a simulation of how our brain works. We create a single neuron, we call it perceptron, and then we create layers of this perceptron, of this neuron, and we train them using some math. Actually, since there's some, you need the functions to be continuous, so we use more a function like this. And then you can create topology. So imagine that each neuron is receiving an input, you have some weights, and depending on the sum of the weight, you give an output or not. And these weights that you see here is what you want to learn and what is making this perceptron understand a model. A single perceptron can only model linear data, so it can split a class using a line. If you use multiple neurons together, then you have more power. In the past, they tried to add multiple layers of neurons. I'm talking about more than 15 years ago, but the computational power was not enough to train this data. So the result was that if you put too many neurons, too many layers, the result was not good, and people was thinking that it was not a good approach. Then when the CPU became more powerful, and also some algorithms started to use the GPU, the graphical processing unit of computers, where you have a higher level of parallelism, they found different ways of training these neural networks, and that's what deep learning is. So it's the possibility of training deep, because you have multiple layers of neural networks, using this new algorithm and the GPU processors that offer a different level of scalability. And what happened is that they just didn't start to create larger and larger networks, but they create different network architectures, because they understood that different models, so different layers of different sites, can solve different problems. For example, a very important one is the convolutional network, is what is used for vision. So the idea is that instead of having a generic brain, I create specific layers that can extract features from pictures, maybe a layer that is extracting squares, so it's checking if in a picture there are squares, or checking if there are circles, or checking if there are faces. So different specific layers. And then you can project and put all this together to create a much more complex neural networks. And that's what deep learning is doing. So this is, you see the single perceptron is at the top left. It's a single neuron getting feedback. Then the feed-forward approach was common a few years ago. It's just adding a few layers. But then you see people started to create crazy connections among these perceptrons, among these virtual neurons. And each one has usually some benefit, some specific area of focus where they work better. So we released in open source a library for, it's called Destiny for deep learning. It's publicly available on GitHub, and it's actually slightly different from other areas in other libraries in the deep learning space, because it's focused on recommendation. It's something that we in Amazon do a lot. So it's focused on recommendation. It can scale on multiple GPU inside a server or on multiple servers. Can use large layers, because when you do recommendations, you imagine you have a very big matrix where on one side you have all the customers, on the others you have all the products. And you can imagine as Amazon, we have a lot of products and a lot of customers, so the matrix that you get is huge. And with recommendation, this is a difference compared to computer vision or audio recognition. You have sparse data. So in this big matrix, you have a lot of zeros, because there's a lot of customers that are not interested in all the products of Amazon. Only each customer maybe has a subset of products they are interested. So in this big matrix, you have sparse data, a lot of zeros. And this has been designed to be very fast in this use case. So we have some benchmark that shows how it can scale very fast. And we just recently announced a new kind of instances. So this is our virtual server, Amazon EC2, that can offer up to 16 NVIDIA K80 GPUs inside a single server. So this is the kind of hardware that you can use for a large-scale deep learning process. Consider that these kind of instances start at 90 cents per hour. So it's even if you see big numbers here, it doesn't mean that if you want to invest $10 or $20, you can build and train your own deep learning model. At least you can start. So we see this other approach. And let's see how you can put everything together and build a smart mobile app. So let's imagine this is the mobile of some user. You can use services that we offer for authentication. So we have Amazon Cognito. The user can authenticate or trust an external authentication, such as Facebook or Twitter. And then we have a service where you can send all the information on how the user is using your application. So you can collect information and understand which features are used, which are not. And you can store this information on our object storage, Amazon S3. Now that the data is on Amazon S3, exactly the same tool that I was trying to use at the beginning and was not working because I was looking at the wrong region, you can also load the information on a database and explore it. And from this to-date repository, you can create a model, exactly as I did before. So you can link the data and create a model of this data that can model how the user are using your application. And then you can enable the real-time predictions. And your application can call this API to understand what the user can do next. For example, one thing that I like, and it's not very common, I think it can help an application to be more useful, more easy to use, is a dynamic UI. So every time, sometimes there's some hidden options that you have to scroll or find. Maybe if you understand that a user is often using this option, you can change the order of a menu, you can change the order of a user interface to put the options that the user is more interested more prominently in the user interface. And you can also call AWS Lambda, our serverless function service, where you can launch functions that can also call these predictions to optimize the output and the result and send back some result to the application using SNS mobile push, so mobile push notifications. You can also stream data, so this is something that you can do very easily. For example, the location of the user. So you can, if the user gives his agreement, you can send every 5 minutes the location of the user. The Lambda function can check, and maybe depending on the location, you can optimize and show the content that is available in that location. And you can also use other tools to store this information as well. So one idea when you see all these services that I put in this architecture is where are the servers? So here there are no servers. I'm always using high-level services that we offer. And you can build an event-driven model where you drive the links among the services so that one service is triggering another one. And you don't need to install operating system, patch systems. You can just build a prototype and scale an application in production out of these high-level services. You can interface using SDKs, CLIs. We have different tools. And probably my suggestion, if you want to build a new smart application today on a cloud platform, think of the cloud platform as a provider of services, not a provider of servers. Thank you.